Hi everyone, welcome to our YouTube channel, Best Science Brain YouTube channel. Today we are going to present a tutorial on advanced organic chemistry. The topic we have today is inductive effect and mesomeric effect. And these are the key topics in organic chemistry that determine electronic transmission from one atom to another atom or from one bond to another bond. If you are seeing this channel for the very first time, kindly subscribe to the channel by tapping on the subscription bell. The video is playing. Located beneath the video, you have the subscription bell or icon. Tap on it once and get subscribed to the channel. Then this video is mainly for those in high institution, mainly in second year of high institution as organic chemistry, and also for those who are doing their postgraduate or master's degree in organic chemistry. So this tutorial is also good for you and also for teachers or lecturers in chemistry in high institution. We know that education is a continuous process, it does not stop at one stage. So today we're going to have a lecture in organic chemistry, and this lecture will introduce us into organic reaction mechanism. So as I said, we're looking at inductive effect and mesomeric effect. So kindly like our videos, share our videos to fellow undergraduates or postgraduate students. Let them follow us in this YouTube channel. So we have inductive effect. Represented using I, called the I effect. We also have number 2 effect called mesomeric effect. Represented using M or M effect. So when we use the I, it means inductive. When we use M, it means mesomeric effect. And that name for mesomeric effect is, can say call it mesomerism or resonance. So when you hear of the word mesomeric effect, mesomerism or resonance, they all refer to the same terms. So these are two terms in chemistry, mainly organic chemistry, that determine the stability and reactivity of organic compound. So we're going to start with the inductive effect. So the inductive or I effect. So we say that this is an effect that leads to the polarization of electrons via sigma bond. So for us to understand inductive effect very well, we have to understand what is meant by sigma bond. Sigma bond in chemistry, or written in this form, so that is sigma bond. So we have to understand what is meant by sigma bond in chemistry and how to throw some light on covalent bonding. So sigma bond is what you also known as single covalent bond. That is single bond between two atoms. So these bonds are called sigma bonds. So when we use the word sigma bond in chemistry, we refer to single bonds. Now, having done that, let us demonstrate how single bonds are formed before we now start talking about inductive effect. So let's think of a molecule like chlorine molecule. Chlorine molecule consists of two atoms. So for your basic chemistry, general chemistry in phase A of higher institution, or whether it's polytechnic or university or college education, you must have learned bonding. So let's look at bonding chlorine atom. So each chlorine atom has 50 electrons. So these 50 electrons have 287, 2 in the K shell, 8 in the L shell, and 7 in the M shell. Also for this one, 287. So we share the electrons. So each of the chlorine atoms, so we have chlorine, 7 electrons in the outermost shell shared around the chlorine, following the Lewis electron structure. So this is 1, 2, 3, 4. Remaining 3. We now pair 5, 6, 7. So that is chlorine with a 7 valence electron. And the other chlorine atom again with 7 electrons. We can use star for this 1, 2, 3, 4, 5, 6, 7. So you see that chlorine being a non-metal will require electron. We accept electron to complete its outermost shell. So this one requires 1 electron to make it up to 8. This one requires also 1 electron to make it up to 8. So in bonding, the 2 chlorine atoms will accept 1 electron. We contribute 1 electron each, one from this chlorine and one from the other chlorine, to form a single bond, which is also known as sigma bond. So you can see this. So you can see that. So you see a bond formed. So this is the bond pair. We call it bond pair in chemistry, or shared pair of electron. So a bond pair of electron constitutes a single bond, otherwise known as sigma bond. So we can draw chlorine in this form Cl. Replace the bond pair with a slash. That slash is a single covalent bond, otherwise known as sigma bond. So the electron shared is sigma bond, while this one that are not used in bonding, 1, 2, 3, 4, 5, 6, we call them lone pairs, lonely on their own. So if you look at this example here, we have a sigma bond formed between 2 chlorine atoms. Now the question is this: can inductive effect occur between 2 chlorine atoms? The answer is no. We don't talk about inductive effect in a covalent molecule that contains similar atoms. Just like when you have hydrogen, you cannot talk about inductive effect in hydrogen molecule because these atoms have equal electronegativity or equal electropositivity. So sigma bond occurs when, let me write it down, when we have a covalent bond between 2 atoms of different electronegative difference. So we can say that inductive effect occurs between 2 atoms of different electronegativity. So you don't talk about inductive effect when you have atoms of similar electronegativity. For instance, let's look at carbon linked to chlorine through sigma bond. So look at this structure. So here we can talk about inductive effect here because chlorine has a greater electronegativity compared to carbon. Remember, for your basic chemistry, chlorine is in group 7, is a halogen, and halogens are the most electronegative elements. So that means there's going to be a tug of war between this carbon and this chlorine. Let's number them: carbon number 1, number 2, and number 3. So, or let's start this with number 1, 2, and then 3. So there's going to be a tug of war between this carbon and chlorine. What kind of tug of war? They're going to drag this electron share between the 2 of them. So which of them going to have the upper hand? Chlorine will have the upper hand in dragging the electron. Why did I say so? Because chlorine is more electronegative than carbon. Let's assume that we have only carbon atoms in the structure. Carbon 1, 2, and 3. Let's consider these 2 positions. This carbon and this carbon. Why are we not going to have another effect in this situation between 1 and 2 or between 2 and 3? It's because these atoms have similar electronegativity or electropositivity. So if electron is shared, a sigma bond means 2 electrons share between the 2 carbon atoms. So these are the 2 electrons. So let's assume that the distance between the nucleus of this carbon and this one is 1 inch. 1 inch. The distance between the nucleus of this carbon and the electron will also be the same, 1 inch. So none is cheating the other because they have equal electronegativity. But should I replace this carbon with chlorine now? Because chlorine is more electronegative than carbon. That means electron will drag between this chlorine atom and this carbon. And because chlorine has a higher electronegativity, that means chlorine will pull the electron closer to itself than carbon. What it means is that maybe perhaps the distance between carbon, the chlorine nucleus and carbon and the electron, could be 0.5 inch, while the distance between carbon and this one could be maybe perhaps 1 inch. That means as you observe, you see that chlorine, the electron is closer to chlorine compared to carbon. But can chlorine take the whole electron away? The answer is no, because the bond here is covalency. So carbon will still partake in the sharing of electron, but it will be that chlorine is put electron closer to itself than carbon. And that leads to polarization of the bond, making the bond polar or somehow soluble in water. Such bond, such effect, what called inductive effect. So looking at this example now, or this illustration, we look at chlorine, we look at carbon. Because chlorine is more electronegative than carbon, the electron will shift closer to chlorine than carbon. We now give chlorine atom partial negative sign. Because we know in chemistry, when an atom accepts electron, it becomes totally negatively charged. But because it appears that chlorine is draw electron closer, but not totally belonging to chlorine, we now say that chlorine is partially negatively charged. And carbon appear to be losing. And in chemistry, when an atom appear to have lost electron, we say they're going to have a positive charge. So because carbon appear to be losing these two electrons, we now give it partial positive charge. So we can now draw an arrow here. This arrow shows that electron is drawn by chlorine, it's taken away by chlorine. So chlorine is taking the electron away from carbon. That means this arrow shows the electron is moving to chlorine, not the other way around. It's wrong to draw it this way, because if you draw it this way, it means that chlorine is losing to carbon. But the arrow pointing toward chlorine means that chlorine is taking away the electron from carbon. So we now say that chlorine have what we call a negative, this is I, a negative inductive effect. I minus, a negative inductive effect, because atoms or groups that tend to pull electron away from another atom are said to have negative inductive effect. So on the whiteboard, we have groups that have negative inductive effect. So the groups that normally retrieve electrons or pull electron density away from carbon. So as mentioned, chlorine initially. So all the halogens, you can see the halo groups, fluoro, chloro, bromo, and iodo group. The halo groups have negative inductive effect. They pull electron away from carbon. So if I should have maybe chlorine or even fluorine here, so fluorine or any of these will acquire partial negative, while the carbon will acquire partial positive. We'll pull electron away from carbon. So it's because it has a negative inductive effect. And then we also have the hydroxy group, which can still come in place of fluorine, or this is the alkoxy group, that the ether group can also be here. We have the mercapto group, and then the SR group. We have the amino group, we have the IQ amino group, we have the IQ amino group, we have the nitro group, we have this is the aldehyde or carbonyl group, we have the ester group, we have the carboxylic group, we have the amide group, so carboxylic group, we have the ester, have the carbonyl group, have the amino group. Sorry, it's not amino, it's nitro group, amino, AQ amino group, diAQ amino group, mercapto group. They will have this is called the carbonyl halo, because that S stands for halogen, halo carbonyl group. So all these groups are electron withdrawing group, or negative, they have negative inductive effect. So we can call the electron withdrawing groups. So when they are attached to a carbon atom, they tend to pull away electron from the nearby carbon atom, making them to have partial negative charge and make the nearest carbon atom to have partial positive charge. We have to know that inductive effect oppressed in a short distance. That is, it's oppressed within maybe 2 or 3 bonds away from the electronegative or for the electropositive element. So after the second carbon, the inductive effect tends to decrease in its intensity. So this will have inductive effect. This one, we can put this one as that is DD for the second one, and this one partial sign for the third one. So the inductive effect tends to decrease with distance. So that's the way it goes. So this is electron withdrawing. So this one will withdraw electron from this. This tends to withdraw electron from this, and this one tends to withdraw electron from that. So making it so as we move away from this one, inductive effect tends to decrease. So stay connected as we continue. So can we have positive inductive effect? Yes. We can still have positive inductive effect. This occurs when an atom or group tends to donate electron to the adjacent atom. For instance, let's look at this carbon chain. And let's have a group here. And the name of the group, let's call the group G attached to that end. So if carbon is more electronegative than G, what then happens? The carbon will pull the electron away from G. So you see that arrow going this way. So moving this in this way, in the direction. Carbon atoms pull the electron away from G. So that make G, you know in chemistry, when an atom loses electron or when a group loses electron become positive charge, that makes G become partially positive. I'm making this carbon to be partially negative. 1, partially negative. 2, partially negative. 3. So this situation is, so we now have a positive inductive effect. And any group which is involved in this situation or which has a positive inductive effect, any group or atom is said to have what's called electron donating effect or electron releasing effect. While the one we stated previously, like the halogens, the nitro group, those ones have negative inductive effect because they more electronegative than carbon tend to pull electron away from carbon. But because carbon has an upper hand here, carbon wins the war by putting electron closer to it, while this one appears to be losing. Now, what kind of groups normally have a positive inductive effect? Normally, the alkyl groups. The alkyl groups have positive inductive effect. An example of alkyl group, in chemistry, from your basic chemistry, an alkyl group is a group formed when an alkane loses one hydrogen atom. For instance, methane, when it loses one, it forms methyl. So this methyl is an alkyl group. So in terms of alkyl group, we can classify them into tertiary, secondary, and primary alkyl groups. For instance, this is a tertiary alkyl group where you have 3 alkyl group bonded to the central carbon. So it can be negative free radical, it can be a carbocation. So this tertiary or 3 degrees alkyl group. This one's tertiary alkyl group exert more inductive effect than secondary. Secondary alkyl group is when you have 2 alkyl group bonded to the central carbon. So this is called secondary alkyl group or 2-degree alkyl groups. Then we can also have primary alkyl group. That is when you have only one alkyl group, methyl group for instance here, bonded to the central carbon. This is said to be primary alkyl group or 1-degree alkyl group. Then we can now have the methyl group, CH3, or the methyl cation. So you see that in terms of positive inductive effect, the tertiary alkyl group, an alkyl group whereby the central carbon is bonded to 3 different alkyl groups, is called said to be tertiary 3rd degree, has a greater inductive effect than the secondary alkyl group, which have a greater effect than the primary, and so on. So if we should have a tertiary alkyl group at this point, that is some of this nature. So this sentence has this. So that means this will have a greater effect compared to when you have secondary or when you have primary alkyl groups. So that is, they'll have what they're going to release electron to carbon because carbon is more electronegative than them. So why is the tertiary alkyl group said to have a greater inductive effect than primary or secondary alkyl group? Because of some circumstances like what we call hyperconjugation. Hyperconjugation, the central carbon is surrounded by more hydrogen than than you have in secondary or primary. So the hydrogen atoms are willing to release electron to the empty p orbital of the central carbon. That's what is known as hyperconjugation. So the tertiary alkyl groups experiences higher hyperconjugation than secondary and primary. That is why the tertiary alkyl group exert higher inductive effect than any other alkyl group. So that is what is meant by positive inductive effect. So, what are the consequences of inductive effect? The inductive effect one. So, look at the effect of inductive effect. What are the effects of inductive effect? Number one, it leads to permanent polarization of the molecule. Number two, the negative inductive effect leads to a greater polarization of the molecule, because in this situation the leading element acquires partial negative charge by drawing electron closer to itself, while this one acquires partial positive charge. Then the positive inductive effect leads to a lesser polarization of the molecule. Why? Because let's complete this. Because in this one, let's say we have an atom G here. The carbon atom close to this one appears to be more electronegative than this one and draws the electron more to itself, making this one become partially positive on the losing side. This one partially negative, and then partially negative. So that is all about inductive effect. We're going over now to the next effect, which influences the stability of molecules, which you call mesomeric effect or mesomerism. So we look at another effect, that another phenomenon that affects the stability and reactivity of molecules, organic molecules, known as mesomeric effect or M effect. I say call it mesomerism or resonance. So, unlike inductive effect that occurs in single bond or sigma bond, the mesomeric effect occurs in double or triple bond, which we normally call pi bonds. So we'll say this is the polarization of a molecule due to the delocalization of electrons. The word delocalize means shift in position of pi electrons in a conjugated system. So, what do you understand by pi electrons? Pi electrons refer to electrons that make up the single bond or the bond written as pi, or sometimes with the symbol, mathematical symbol pi electrons. So, like this kind of electron that make up we have in alkenes is a pi electron, double bond. And then also in triple bonds, we also have pi electrons. So that one we'll talk about pi electrons. They refer to double or triple bonded compounds. So mesomerism occurs between two pi bonds. or between a pi bond and a lone pair of electrons. So for us to talk about Mesomeric effect, it must occur either between two pi bonds or between a pi bond and a lone pair of electrons. It does not occur in sigma compounds, bonded compounds coupled with single bonds. And also, we should also know that it does not occur in any compound that has double bond or triple bond. It must occur in a compound that is conjugated. So what do we mean by conjugated system? What is meant by a conjugate system? It's a system whereby the single bond and the pi bond alternate with each other. For instance, let's look at benzene. There's reason will occur in benzene. Why is this? Look at benzene structure. Have this, have that, have that. So benzene is planar and is also conjugated. So why do they say it's conjugated? Because we have a double bond here. This is a double bond or pi bond. This is a single bond, double, single, double, single, double, single. So double bond alternating with single, but after each double bond, that is a single bond. Or between two double bonds, that is a single bond. Or between two double single bond, that is a double bond. Go round it. That is what is meant by a conjugated system. So that system must not be cyclic anyway. So we can still have a system like this. Somebody asks, can mesomerism occur in this kind of system? The answer is yes. You see a single bond, double bond, single bond, double bond, single. So this system is also conjugated system. So any system of such nature that is conjugated can have mesmerism occurring or resonance occurring in such a system. And resonance tends to increase the stability of the molecule, number one, and also tends to reduce the energy of the molecule. And that is the energy of the molecule is reduced. The lower the energy, the higher is stability. So, having done that, so we'll now take an illustration of what is meant by resonance or mesomeric effect. Let's look at this system that is conjugated. So, how are we going to move the electrons? So, electrons will move from, remember I told you, can move from here to there. So, when this happens, this one can also move from here to there. So now I have this, when electron moves, this one becomes negatively charged. Remember, as we said in chemistry, a bond means two electrons. So that will give this one negative charge, then this, and then this also move down to that side, negative charge. So at the end of the day, we'll see move again. This one will move again to the next position. This one move to the next position. So now I have this single bond here, double bond. This one coming back to that position, and then this single bond here, and then this one moving over there to give you a double bond. If there's an atom over there, it continues to move. So at the end of the day, this carbon here, that's the original position, this is the first carbon, has lost an electron that is shifted away from it. That means this carbon to become deficient in electron. When I give this carbon positive charge, because it is losing electron. The electron has been removed from it. It now becomes deficient electron. So have positive end here. So these are an example of mesomeric effect in a molecule. We're going to take more examples of a mesomeric effect. Before we demonstrate the mesomeric effect on some molecules, we still have to point out that just like we have the I negative inductive effect or negative inductive groups, that is negative I group and also positive I group, electron withdrawing and electron donating groups. We still have also the negative mesomeric groups or effect and also the positive mesomeric groups. So you can see the nitro group is a negative mesomeric group or has the electron withdrawing effect, the cyano group or nitride group, the aldehyde group, the ester group, the carboxy group, the halo carbon carbonyl group, the amide group, and the ester group. So this is the this is the carbonyl group. Sorry, why this is the alkanoate or ester group. So all these have negative mesomeric effect, resonant effect, while these groups have positive mesomeric effect. That the halo groups, fluoro, chlorobromo, iodo, hydroxyl, the amino group, the IQ amino group, the di-IQ amino group. You look at this very well. You see that all these groups, we have mentioned them before when we did another effect. All these groups classify under negative mesomeric group and positive. All of them fall into negative inductive group. Remember, you can review the video. Negative inductive group, all of them are classified into negative inductive group. But if you separate some of them belong to negative mesomeric group, while some belong to positive mesomeric group. But in all of them are under negative mesomeric group or effect, electron withdrawing group for mesomeric for inductive effect. Sorry, all of them are classified as negative inductive group. So, but you can group them, part of them as negative mesomeric and positive mesomeric. But in all, they are all negative inductive effect groups. So having done that, the next thing we're going to go to is now we're going to illustrate inductive effect in some molecules. So for instance, let's look at bromobenzene. Bromobenzene has the formula C6H5Br. If I draw the structure of bromobenzene, this is the benzene ring. The benzene ring, which is a kind of hexagon with alternating double, single, double, single, double, with the bromine atom on it. So this is the phenyl ring. So I have bromine atom. And you know bromine is the halogen. So halogens have 7 electrons in the atomos shell. So we have 2, 4, and then 6. I use the remaining Y electron to bond with carbon here, making it 7 electrons. So if you understand the bonding sequence, so there's carbon at this end. So carbon brought 1 electron, bromine brought 1, making a double bond. A single bond, sorry, then you have the remaining 6 electrons out of the 7 valence electrons in bromine. So to demonstrate mesomerism or resonance in bromine or in bromobenzene, we have to shift this electron. Remember that bromine belongs to a positive, one of the positive mesomeric group, that's the electron reducing group. So you're going to read electron to this bond here. When we shift the electron, then this bond here will be shifted also to the next or adjacent carbon atom. At the end of the day, we now have this structure produced, which is the resonance structure of bromobenzene. We now have bromine now, having now remaining 4 electrons. And this electron will be shifted here, it becomes a double bond. And because bromine has lost electron, is now electron deficient, has lost electron, now becomes positively charged. So like a cation. While this electron here shift to this point and become, you have it here at this carbon, making this carbon negatively charged. So you have the resonance structure of this. We use double-headed arrow to show that. Also, for this one here that we produce here, we can still continue the resonance. This electron here on this carbon can shift to this bond to join this, while this one shifts to the next adjacent carbon. So you have to learn how to draw resonating structures. It's very important in organic chemistry. Very important in organic chemistry, how to draw resonating structures. So you now have this maintain bromine, be electron deficient, show the electrons, positive charge. Then this one entering this point, joining this point, while the electron leaves this pi electron, this to stay at the position, and then you have this there. Also, we can still get another resonating structure. What do? We shift this electron now into this point, while this electron here shifts to this point. So we now have a structure drawn again. We have this drawn. We have bromine. two electrons or four electrons around it, deficient, an electron positive ion. You have this. Then this electron here shifts to make a pi bond here, while the pi electron here shifts and making this carbon to become electronegative. So you can see that we have about, you can count it, 1, 2, 3, 4. So I can still move again to move this bond into okay, or it's okay now. 1, 2, 3, 4. Four resonating structures of bromobenzene. And you have to know that resonating structures, none of them satisfies the structure of bromobenzene. Rather, we can see that the actual structure of bromobenzene is the hybrid or a kind of combination of the whole resonating structures. Is a hybrid of this. So none of them actually satisfy the true structure of bromobenzene, but the actual structure lies within the four of them. We say it's a hybrid of these four resonating structures. So what is resonating structure? Resonating structures are Lewis structures which show the delocalization of the pi electrons from one bond to the other. So we call them resonating structures. So we'll take another example. So number two example we want to use is phenol, known as hydroxybenzene. That is phenol. Formula is C6H5OH. So we want to demonstrate mesmerism or resonance in phenol. So we have phenol structure drawn. This is the phenyl group, which is C6H5 group, which is a kind of group obtained when benzene is one hydrogen. We draw the benzene structure. So that is this. Then removing one hydrogen here, we'll now bring in OH. That is the phenyl group. You know that oxygen in chemistry, has 6 valence electrons. So having 6 valence electrons, I use one electron to bond with hydrogen. One electron used to bond with hydrogen here at this point. On remaining one used to bond with carbon here, remaining 2. One electron for bonding here, and one electron for bonding, remaining 4 electrons. And 4 electrons constitute 2 pairs. So that is the actual structure of phenol. So to demonstrate resonating structure of phenol, we have to shift this electron. So the hydroxy group is a positive mesomeric group. So when we shift the electron, we also shift this one to a different position. So we now have the next resonating structure of phenol drawn. Here we have the oxygen here. We now lack 2 electrons. I mean, 2 electrons is shift away from it. So that the 2 electrons here, making the oxygen to be electron deficient when I give the oxygen partial positive charge. So electron now moves to this point. You see that? The structure changes. You have the resonating structure for phenol. Then also, we can shift this electron here to be in this, to form a pi bond here, while this one shifts to this point. So we now have this produce. We have that structure produced. We have the oxygen, electron deficient oxygen atom or hydroxy group up. Then we have a pi bond formed here, and then this carbon here becomes negatively charged, and there you have that. You can see shift again. This one moves to this point, while this one goes to that point, the adjacent carbon atom. We now have this structure produce. So you have that. This bond locates itself here, while this bond goes there to make this carbon negatively charged. They have this produce. So we have that. So you can see the resonating structures of phenol. None of the structures actually represent the actual structure of phenol, but we can say that the structure of phenol is a hybrid of these 4 structures meshed together. So we have resonating structure of phenol or hydroxybenzene drawn on the board. So as a student in high institution, this is one of the key aspects of organic chemistry or organic reaction mechanism. Before you go into organic reaction mechanism, you must then understand the mesomeric effect and the inductive effect. The next compound we want to consider is amino benzene, aminobenzene. So the third structure is aminobenzene, a compound also known as aniline. Formula C6H5NH2. So let's draw the structure. We'll draw the benzene ring or the phenyl ring. We'll have it drawn here. So show the bonds in benzene alternating themselves. Then the amino group is up there. You have that hydrogen, 2 hydrogen atoms. So let's look at electron. Is there an electron, lone pair of electron on nitrogen? Remember I told you that mesomerism can occur, can involve shifting of the double bond or shifting of the double bond and the lone pair. That's what I said initially in this video. So this nitrogen, atomic number is 7, which is 2, 5. So nitrogen has 5 valence electrons in this atomic shell. So it uses 1 here to bond with hydrogen. It brings 1, hydrogen brings 1. This one brings 1 again, hydrogen brings 1, brought 1, and carbon brought 1. So I use 3 for bonding, remaining 2 electrons now. So we have a pair of electrons not used for bonding, a lone pair that will shift now. So let's look at the resonance structure. The lone pair shifts to the nearest bond, sigma bond here, and then this one shifts to the adjacent carbon atom. So that will give us a structure of this nature. We have a resonating structure of this nature. We have double bond form here, nitrogen, hydrogen, and then hydrogen. So this nitrogen here is now electron deficient, having lost 2 electrons, so it becomes positively charged. So this electron shifts to this point, the adjacent carbon, making this carbonated charge. Then we have this, we have that. So this also, let's get another structure. This one shifts, shift to the nearby bond, while this one shifts the adjacent carbon. So now have this produce again. So we'll have that produce. So you're going to have a bond form, a pi bond form here, while this one shifts to make this carbon negative. So you have this structure produce. So this is the positively charged amino group over there. So this electron will also shift the nearby bond to make it a pi bond, while this one shifts to the adjacent carbon atom. We now have this produce. We have that, this bond. Then this become double bond. Then this is a electron. This carbon becomes negative charge, and then this is the amino group, which is positively electron deficient amino group, which is positively charged, which has a positively charged nitrogen atom, and so on. So you have the resonating structures of aminobenzene on the board. And look at the structure very well. The rule of conjugation is obeyed in all of them, so you can see that very well. So we'll go to the next example. So move to conditions for resonance or mesomerism. There are 2 major conditions for a compound to undergo resonance or be engaged in resonance or mesomerism. The first is conjugated system. So there must be a system of alternating single and multiple bonds or lone pairs adjacent to each other. Just like the examples we took so far, those compounds are conjugated. So it must be a system containing alternating single and multiple bonds, or that will presence of lone pair electron adjacent to each other. Then the next condition is planarity. The molecule ion must be planar or nearly planar to allow for overlap of p orbitals or lone pairs. The molecule ion must be planar or nearly planar to allow for overlap of p or lone pairs, p orbitals or lone pairs. So next, we'll go over to the significance or the importance of mesomerism. Now we're looking at the significance or importance of mesomerism or resonance. The first point here we have is stability of molecules. Resonance leads to molecules becoming stable by lowering their energy, and as we said, the more the more the more resonating structures a molecule can have, the more stable the molecule becomes. So a molecule that has a higher resonating structure is more stable than the one that has lower resonating structures. We go to number two. So number 2 point is reactivity. So understanding resonance helps us to predict the reactivity of organic molecules, especially in aromatic electrophilic substitution and also aromatic nucleophilic substitution reactions, which we're going to study when we move to reaction mechanism. So number 3 is acidity and basicity. So resonance helps to or influences the acidity and basicity of organic molecule by either stabilizing or destabilizing the conjugate base. For instance, phenol, which is aromatic alcohol, is more stable compared to aliphatic alcohols like ethanol, methanol. So phenol is more stable due to stabilization of the phenolzide ion by resonance. Number 4 is bond length. So resonance gives a kind of partial double bond, whereby no bond is considered as purely single and no bond is considered as purely double. Just like in benzene, whereby we cannot say that in benzene that the double bonds in benzene equivalent to the ones you have in alkenes, because in benzene, that's why sometimes you see benzene structure drawn this way. So that is, we assume that the double bonds are equal in length. So, or the bonds in benzene are all equal in length. So, because of resonance. So, because of resonance, the bonds are considered to be equal in length in the benzene structure. So, that is making the bonds to be equal, or what's called equalization of the bond lengths. So, that is it. So we're going over to limitations of mesomerism or resonance. The first is non-real structures. So what do you understand by this? What I mean here is that the resonance structures or resonating structures are not real and do not represent the actual structure. The actual structure is a hybrid of resonating structures. The second limitation is applicability. That's another limitation for mesomerism or resonance. Well, know that mesmerism is only applied to conjugated systems or system containing alternating single, double bonds. So that is what by it cannot be applied to compounds or to all compound or the compound that contain only sigma bonds. So it has limited application. So having done that, we now look at what the difference between resonance and inductive effect. Inductive effect applies both of them. What the similarity, first of all, both of them leads to the polarization of molecules. What the difference? Inductive effect deals with polarization of molecules due to electronegativity difference between the two atoms bonded by a single bond. What it means also that inductive effect also only occurs in sigma bonds, that is single bonds. Why mesomerism or resonance occurs in conjugated compounds or between a pi bond and a pi bond, or can occur between a pi bond and a lone pair of electrons. It does not occur in single or sigma bonds. So that is it. In the next or in the next session of this class, we're going to look at some questions, multiple choice questions on this particular topic, resonance and mesmerism, and then see how can treat these multiple choice questions to have a strong background in this aspect, inductive effect and mesomeric effect of organic chemistry. If you have not subscribed to the channel, tap on the subscription button, share our videos. We thank our viewers all over the globe for your efforts in subscribing and also viewing our video and also sharing our videos. So keep on watching as we move to the next session of this video. In this session, we're going to look at practice questions on inductive and mesomeric effect. So these questions will help us understand more on how to solve problems on these two key topics in organic chemistry. based on the video or the lesson that we already watched. So number 1 says, which of the following best describes inductive effect? Option A, delocalization of electrons through a sigma bond. Option B, transfer of electrons through space. Option C, polarization of electron density along a sigma bond. Option D, resonance stabilization of charge. So look at the options. Which one do you think is the answer? A is close to the answer. Delocalization of electrons through a sigma bond. And also C is close to the answer. Polarization of electrons density along a sigma bond. We cannot talk about inductive effect without mentioning polarization, and it must occur along a single bond or sigma bond. So the correct answer is option C. Option C is the right answer to number 1. Go to question 2. The following groups exhibit the strongest electron withdrawing inductive effect. Option A, methyl group. Option B, fluoro group. Option C, chloro group. And option D, hydroxy group. So if you look at the options, from our lecture, we gave groups that can exhibit or that can cause negative inductive effect. That is, groups that can withdraw electron from carbon or nearby atoms. And those groups should be highly electronegative. So let's look at the options. A is methyl group and alkyl group. Alkyl groups do not withdraw, rather they donate electrons. So they cannot exhibit strong electron withdrawing effect. So A is off. Then we look at option B, C, and D. Those are electronegative. So B, C, and D, and hydroxy, that is fluorohydroxy, can exhibit electronegative or electron withdrawing effect. But we're looking for the one that will exhibit the strongest effect. We look at fluorine, chlorine, and hydroxyl. See that fluorine is the most electronegative element or group among the 3 groups we're considering under option B, C, and D. So the correct answer to question 2 is option B, which is F, or fluoride ion. So option B is the correct answer to this question. So you see it's B. Question number 3. The following species stabilizes a negative charge through resonance. The following species stabilizes a negative charge through resonance. Option A, the methyl group. Option B, the nitro group. Option C, the amino group. And option D, the hydroxy group. So the correct answer to this number 3 is B, the nitro group. So let's throw some light on that. Species that stabilize a negative charge through resonance typically involve the localization of electrons over multiple atoms or through conjugate systems. This delocalization sprays out the negative charge, making the species more stable. Examples are mainly anions. Anions are species that have negative charges. One of the examples is the carboxylate ion, e.g., also known e.g. the acetate ion, which is obtained from ethanoic acid. So why would this ion stabilize negative charges through resonance? So the negative charge can be localized. You can see the negative charge on the last oxygen. So that negative charge on the last oxygen can also move to the second oxygen. Can be localized over both oxygen atoms through resonance, resulting in 2 resonance structures where the negative charge is partially on each oxygen atom. So what do we mean? So look at the structure of the carboxylic ion and see how the negative charge can move from one oxygen atom to the next oxygen atom. So you can see the structure of the ethanol ion. I see the pi bond, which can shift or change its position up, going up, and this electron there can also shift. That is because remember that resonance involves movement of either pi bond or lone pair electron. So when this one shifts, this one can also shift. So initially, this is the one carrying the negative charge. So look at the new structure. So when this electron, the lone pair shifts to this point becomes the double bond, as you can see. And then when this pi bond shifts up, this one now becomes negatively charged. So you see that the negative charge can change position from one oxygen atom to the next oxygen atom, thereby stabilizing this ion. So this ethanol ion or carboxylate ion, ions from organic acids, can be stabilized by resonance, can be stable by shifting its negative charge between two electronegative oxygen atoms. So let's take the next example. Example 2 is acetone, otherwise known as enolate ion. Look at the enolate ion. So enolate ions have a negative charge on the oxygen atom adjacent to a double bond. So negative charge can resonate into the double bond, leading to resonance structures where the negative charge can be either on oxygen or delocalized over both oxygen and adjacent carbon atom. So let's see the structure. So you can see the enolate ion, one of the structures or one of the resonance structures. The carbon here, valence of carbon is 4. Is one electron from a bond here. Use one electron from a bond there, and the electron from a bond on the other position. So repeat it again. The valence of carbon is 4. You have to understand covalent bonding. You use one electron from a bond here, and the electron from another bond there. Okay, so you now have a lone pair of electron. Then this lone pair can be delocalized since resonance involves shifting of the lone pair or shifting of the pi bond. So this lone pair can move to this point, while this pi bond can move over there to make this one negatively charged. So you can see the structural change. When this lone pair moves to this point, the plate becomes a double bond. And then when this pi bond goes up, the plate becomes a negative charge oxygen ion. So the two structures show that the pi bond or the lone pair can shift from oxygen between carbon and oxygen atoms in this enolate ion. So it can be stabilized through negative charges. Other examples are the phenolzide ion, the PHO, and the nitro ion, NO2. So hydroxide ion can also stabilize a negative charge only or especially on aromatic when it's bonded to aromatic rings such as in phenol. So you can see the phenolzide ion where the lone pair also is shifting to form a double bond here, and the pi bond here moving to the adjacent carbon to give a negative charge there. So thereby moving the negative charge from oxygen to the adjacent carbon atom. You can see the difference. This one also can shift and move to to this bond here, while this pi bond will also shift to form a native ion on the adjacent carbon atom. So you can see that. So by so doing, you see that the negative charge is being delocalized from oxygen to adjacent or nearby carbon atoms, showing that the phenoxide ion can stabilize by shifting all the negative charges from one atom to the other. Look at the nitro ion, the NO2 ion. You can see the first oxygen on the left-hand side having negative charge, and oxygen on the right-hand side having double bond. We'll have the nitro ion being positive charge. This is a structure of NO2 ion, and then that structure can have a resonance structure, whereby you have the difference, the two oxygen atoms swapped. So whereby the one on the left-hand side now has double bond for this structure B. So this is structure A, and this is structure B. So you can see the difference between the two of them. So when we say that an ion can be stabilized by resonance, what it means is that the negative charge of the ion can move from one atom to another. It can be between two similar atoms, like two oxygen atoms, changing the negative charge, or between two different atoms, like oxygen and carbon, as we saw in phenoxide ion and also in enolate ion. Question 4 says, which the following statement about mesomeric effect is true? Option A, it involves transfer of electrons through space. Option B, it always leads to resonance, stabilization of charges. Option C, it can stabilize adjacent atoms by delocalizing electrons. Option D is only observed in aromatic compounds. Repeat number 4 again for a clearer view. He says, which the following statement about mesomeric effect is true? A, it involves the transfer of electrons through space. B, it only leads to resonance stabilization of charges. C, it can stabilize adjacent atoms by delocalizing electrons. D, is only observed in aromatic compounds. So mesomeric effect, also known as resonance. So which of the answers is right? The nearest answers are option C and D. C says it can stabilize adjacent atoms by delocalizing electrons. And D says it is only observed in aromatic compounds. So D looks like the answer because aromatic compounds are conjugated. But the answer is not D. Why is it not D? Because aromatic compounds are not the only conjugated compounds we have in chemistry. So if you say aromatic compound, that means you are trying to restrict it only to aromatic compounds. So conjugated compounds must not be aromatic only. So the correct answer we're going to choose is C. It can stabilize adjacent atoms by delocalizing lone pair of electrons. So the answer to number 4 is option C. We go to number 5. That says, which substituent exerts both positive inductive and positive mesomeric effect? Option A, the nitro group. We move to option B, the amino group. Option C, the methyl group. Option D, the fluoro group. So we're looking for a group that exerts both positive inductive and positive mesomeric effect. The right answer is option B, the amino group. So let's throw some light on this. So group that can exhibit both positive and inductive and positive mesomeric effect include the alkyl groups, just like the methyl group, the the alkoxy group, that is OR, the ether group or alkoxy group, the amino group, then the hydroxy group OH, and the ester group, and also the alkyl amino group or dialkyl amino group, and then the phenolic hydroxide group. So in our lecture, you can go through the video again. I listed those groups that can exert both positive and negative, both positive and inductive and positive mesomeric effect. So you can go through the video again. You see more examples. Number 6. In the molecule CH3CH2COOH, that compound is called propanoic acid. Which group stabilizes the negative charge on the oxygen of the carboxylate anion? So A, the ethyl group CH3CH2, B, the methyl group CH3, C, the carbonyl group CO, D, the carboxyl group COOH. The right answer to this question, the group that stabilizes the negative charge, is nothing but the carboxyl group, the functional group, because as we described in question number 2 or thereabout, we say that the negative charge can shift from one oxygen atom to the other oxygen atom, thereby stabilizing the molecule. Number 7. What is the major difference between inductive and mesomeric effects? A. Inductive effect operate through a pi bond, while mesomeric effect operate through a sigma bond. B. Inductive effects are localized, while mesomeric effects are delocalized. C. Inductive effects are stronger than mesomeric effects. D. Mesomeric effects are always destabilizing, while inductive effects are always stabilizing. Look at the options. Option A is wrong, because inductive effect operates through sigma or single bond, while mesomeric effect operates through pi bond. So A is off. So the right answer to the question is option B. Inductive effects are localized because inductive effects occur between two atoms, while mesomeric effect can lead to delocalization, whereby the charges are shifted from one atom to the other. So the right answer is option B. So whereby the electrons are shifted from one atom to the other. So it's option B. Number 8 says, with the following functional group typically exhibit a mesomeric effect: A. Alkyl halides, B. aromatic rings, C. alcohols, and D. alkanes. We know that mesomeric effect occurs in a conjugated system. So the functional group that is conjugated here is the aromatic ring. That is B. Option B, the right answer, just like the benzene ring. Number 9. Mesomeric effect results in A. Redistribution of electron density within a sigma bond. B. Redistribution of electron density through a conjugated pi bond. C. Polarization of electron density along a sigma bond. And option D. Transfer of charge through space. So mesmerism or resonance will lead to redistribution of electron density along a conjugated system or pi bond. The answer is option B. Number 9, option B, the correct answer. Number 10. In which of the following compound does mesomeric effect stabilize the molecule? A. Phenol, B. propanol, C. chloromethane, D. ethine. So when we talk about mesomeric effect, we cannot eliminate a conjugated system. So among these options, the one that bears a conjugated system is option A, the phenol. So the answer to number 10 is A. So that we're going to have mesmerism, shifting of the pi bond. So it's A. Number 11. The inductive effect is more pronounced in A. Polar solvent, B. non-polar solvents, C. aromatic compounds, D. aliphatic compounds. So the answer to this question is D. Aliphatic compound, which normally contains sigma bonds or single bonds. So 11 is option D. Number 12. Which the following substance is most likely to destabilize a molecule through mesomeric effect? The following substance is most likely to destabilize a molecule through mesomeric effect. Option A, CH3 group. Option B, the amino group. Option C, the fluoro group. Option D, the nitro group. The answer to this question is option D. The nitro group will destabilize a molecule through mesomeric effect because it is an electron donating group. An electron withdrawing group, sorry, not electron donating group. Number 13. The following represents a hyperconjugation interaction. A. Donation of electron density from a key group to an adjacent pi system. B. Withdrawal of electron density through a sigma bond due to electronegative atoms. C. Delocalization of pi electrons over conjugated double bond. D. Transfer electron density through a sigma bond to a neighboring atom. So the right answer to this question is option A. Hyperconjugation involves donation of electron density from an alkyl group to an adjacent pi system. So that is option A. Hyperconjugation involves donation of electron density from a sigma bond, usually carbon-hydrogen bond, or carbon-carbon single bond to adjacent pi system. So that is option A. Number 14. What type of resonance structure stabilizes a molecule? What type of resonance structure stabilizes a molecule? A. One that increases electron density at an atom. B. One that decreases electron density at an atom. C. One that does not affect electron density. And D. Resonance structures do not affect molecular stability. The answer is A. One that increases electron density at an atom. That is why groups that have M positive effect are the ones that stabilize molecules in resonance because they give out electrons. So electron donating groups tend to stabilize molecules in resonance, while electron withdrawing groups destabilize molecules. Number 15. Mesomeric effect is observed prominently in A. Alkanes, B. Alkynes, C. Alcohols, and D. Aromatics. So among these options, the one that is conjugated is aromatics. We observe resonance mainly in aromatics. So the right answer to number 15 is option D, aromatics. Number 16. Which substance group is known for its electron donating mesomeric effect? A. The nitro group. B. The cyano group. C. The hydroxy group. And D. The amino group. So the nitro group and the cyano group do not donate electrons. Rather, they withdraw electrons. That means they destabilize molecules during resonance. So the amino group, option D, donates electrons and leads to stabilization of molecules. So the substance that donates electron or is the electron donating substance is option D, the amino group. Rather, option C, the hydroxy group. The right answer is the hydroxy group. So A, B, D are electron withdrawing group. Option C, the hydroxy, the lone pair of electrons is an oxygen. This option C, hydroxy, is electron donating group. So the answer to number 16 is C, option C. So let's throw some light on number 18. The solution to number 18. Say substance that exhibit a mesomeric that exhibits a mesomeric effect, resonant effect that stabilizes a conjugate system. We repeat, subtweens that exhibit a mesomeric effect or resonance effect that stabilizes a conjugate system typically include groups that can donate electron, that electron donating groups, through resonance, thereby delocalizing electron density within the conjugated system. They include the hydroxy group, the alkoxy or methoxy group, the amino group, then the vinyl group, the carbonyl group, the aryl group, and the azido group. So these are the common subtweens that are electron donating. If you look at them very well, they contain highly electronegative atom. So there are electronegative difference between the two atoms. Oxygen is more electronegative than hydrogen. Oxygen is more electronegative than the methyl group. Nitrogen is more electronegative than hydrogen. So consider them very well. You see the difference. And then the vinyl group, we have is electron reduced to the presence of the pi bond, carbonyl group, and so on. So these atoms are electron donating groups. So electron donating group tend to stabilize a conjugate system during resonance because they donate the electron out. So that is it. So from that our question, that means there are two answers there: the hydroxy group and the amino group. So there are two. We're going to revisit it. There are two answers that are possible in that question. Then we'll move on again and say the cyano group, that's CN, and the nitro group are electron withdrawing group. So this one electron withdrawing, and they exhibit positive inductive, positive mesomeric effect, M plus effect. So they decrease the electron density in a conjugated system and making it a deactivating group. So they are not the electron withdrawing group. So okay, the electron withdrawing group and the electron withdrawing group are always negative. Why this one, that the electron donating are positive? Please, sorry for the error. So let's go back to the question. So for number 16, the question will be fettered. So the hydroxy group and the amino group are substances that donate electrons. So C and D are right. Go over to number 17. In the molecule CH3COOH, known as ethanoic acid or acetic acid, the COOH group exhibits A. Strong electron donating inductive effect, B. Strong electron withdrawing inductive effect, C. Strong mesomeric effect, and D. No significant electronic effect. So the carboxyl group is rich in electron, casting a negative via charge. So it will exhibit strong electron donating inductive effect. So if you go through our video, we'll mention those groups or those atoms that exhibit strong electron donating inductive or positive inductive effect. The halogens, and this is among them also. So the answer is option A. The correct answer is rather B, not A, please. B, strong electron withdrawing inductive effect. Because the carboxyl group is highly electronegative, so it's going to withdraw electron from the nearby carbon, that's the carbon on the methyl group. So it will exhibit strong electron withdrawing, so not donating, please, effect. So making the carbon atom to be partially negative charge. So why the one on the methyl group to be partially positive charge? So you're going to exhibit an M minus I minus effect, a negative inductive effect by withdrawing electrons. So the answer is B for 17, not A. Number 18, with the following substance is the most likely to exhibit a mesomeric effect that stabilizes a conjugate system. So as I said, so the substance that will stabilize a conjugate system by mesomerism are those substances that will readily donate electrons. That is, those that have M positive effect. So option A, nitro, B, methyl, C, cyano, and D, hydroxy group. So the one that will actually donate electron will be the one that is really rich in electron. So the right answer is D. So it is stabilized a conjugate system by having an M positive effect, giving out electrons to the adjacent carbon atom. Question number 19. What type of resonance structure typically results in delocalization of electron density? A. One with positive charges on electronegative atoms. B. One with negative charges on electronegative atoms. C. One that involves lone pairs on heteroatoms. D. One that leads to increased bond order. So the right answer here is option C. One that involves lone pairs on heteroatoms. Look at the explanation. Option C, the correct answer. Resonating structures that involve delocalization typically include lone pairs on atoms like oxygen and or nitrogen. Number 20. Inductive effect is observed most prominently in compounds containing A. Aromatic rings, B. Alkynes, C. Aldehydes, and D. Halogens. So the right answer here is option D because of the high electronegativity of halogens. So that is why question 20 is the answer is option D. So you can see that. So having done that, we are come to the end of this lecture, comprehensive lecture on inductive and mesomeric effect involving notable examples and also multiple choice, 20 standard multiple choice questions. If you are seeing this video for the very first time and you are not subscribed to the channel and you're in higher institution or you're a postgraduate student, kindly tap on the subscription button or the subscription bell to follow us on this video as we roll out topics. And then you can also share videos to students in tertiary institutions, your friends in tertiary institutions. You share this because they're doing the same topic, the same courses as you are as a science or engineering student. So you can share